There we go. Hey Matt, how are you, buddy? Oh, wait. Get my stuff set up here again. There we go. Let's see. I'll leave that up. Here we go. Yep, seems to be working. So, tell me, what are you working on? What do you need help with? How far are you? Otherwise, we will do some hypothesis testing today, which is pretty easy to do. Not too hard at all. I think we've got a couple of confidence intervals left, too. But as long as you're doing that, using that spreadsheet, those should go really fast. So tell me what you jammed up on, and what do you want to do for trivia today? So, participation in these things is slacked off quite a bit. So, you know, it's kind of dealer's choice, but if you're one of the only ones sitting at the table, you let me know. Thanks. Hey, Morgan, how are you? So yeah, let me know what you're working on. Let me know if there's any topics you want me to cover today. Otherwise, we're going to go a little fast and furious. So here's where I'm at on my pie. Sorry, I was about to call this thing the COVID wheel. So the pie, and I am plowing through the dark blues. Ready for a 3-year food trivia? Yeah, sure. We'll do some food trivia. Yeah, 3-year nap sounds good. So, well, it is spring break next week, and so hopefully you can get, you know, like a week of sleep in there. Prime the pump, so to speak. And then, what I got, this week, spring break, and then 2 weeks after that left. And so, unfortunately, I think we were so far ahead in this class, but I was looking at the video series from last year, and this time last year I was actually on regressions. And so we are about a week behind. And I think that probably happened because we switched to doing the labs on Wednesday, which very few people have been showing up to. And so I think after the break, we'll just go back to doing live streams. Yeah, so we'll do 1, 2, and then 3. Because the last week is finals week, and so technically we only have one meet that week, and so that way we'll get to where we want to go. Yeah, I'm excited too, man. So, although I'm teaching summer classes, they're all online though, so that'll be pretty straightforward. I have gotten a couple of people who asked me, it's like, oh, are you going to do the same class online during the summer? And the answer to that is no, so do not fail this class. I know you guys won't, but so the stats version of the class, the version of the stats class that I'm teaching during the summer is 6 weeks long. It is going to be brutal. All right, so that is. I mean I'm writing it again right now, and I'm just looking at it. You know, this is crushing this class. This is a 16-week class. You're crushing it down to 6 weeks. That class is going to be awful. All right, so it's so much work in such a little amount of time. So, you know, make sure that you get your pie done and things like that here in the next couple of weeks, so you don't have to. So I don't have to see you again during the summer. Like I said, those of you on here, I'm not worried about you. So there are a couple people in the class I'm very worried about, though. But anyway, that's neither here nor there. All right, so yeah, if there's something you want me to cover in Alex today, definitely post it in there. Otherwise, I'm going to go fast and furious through what I've got. We'll do food trivia. That sounds good. today. And then, like, what kind of food? Just like general food or like junk food, or we've done breakfast cereals in the past. So the labs are just the things that I'm doing on Wednesday with show up, ask questions if you got it. And so like I think I've had 3 of them now where there's like one person who's actually showing up, and I mean we crush out a ton of topics in those days, but I mean again, they're nobody's coming back to campus, and so that's fine. And the Zoom thing, it didn't work. Well, no, actually, for this class, it did work last week, and so that's what I'm talking about. It's not extra assignments and stuff; it's just there to help you. But no more assignments, man. I don't add stuff to the syllabus after it's writ. So, I know other people do, but I don't. So, but anyway, here we go. So yeah, if there's a topic you want me to cover today, let me know. Otherwise, we are going to continue with my pack here, which confidence intervals. I think I got 4 of these. So I got 1, 2, 3 that are left on confidence intervals, and then we can start doing hypothesis testing. So I want to get through at least like 6 or 7 topics today. So let's do these confidence interval ones. So last week I did the one with the the standard normal distribution. So if you know how to do that one, then the rest of these are just as easy. And so the only one that's got a little bit like a change to the formula is this guy right here, confidence interval for population proportion. But the t-distribution is just about the same. Same thing with choosing appropriate sample size. This one's really easy. So we'll save that one for last here. But let's go ahead and do this one with population proportion. Now, again, there's 2 ways to do these. You can do them using this formula here, which looks complicated but really isn't. Or you can go over here to course modules, click on this, and then distributions and confidence intervals. Here's my confidence interval spreadsheet. You can use this, all right, to do all of these. All right, I'm just going to show you how to do them in Alex with the calculator because it's really easy. All right, so with the proportion, when we're doing a confidence interval, remember we're using normal distribution. Confidence interval basically says that we can predict with some confidence where a population mean is based upon the fact that all we have is a sample. With proportions, it's part of a whole, and so we use the Z formula with these. It's really, really straightforward to do. The only thing that people do get confused on this one is this concept right here called P hat. And P hat is just the proportion. And so look at this one. It says 207 of whatever stayed together out of 250 cultures or couples. And so P hat is just 207 divided by 250. It's the part divided by the whole. That's your proportion right there. So when we talk about P hat, that's what we're talking about. All right. And so the formula to do a confidence interval on this one is just the proportion plus the confidence level, which in this case is 90%. All right. So 90% confidence level times the square root of P hat, which is the same proportion, times 1 minus P hat, which is the proportion, all over sample size. So it's really easy to do. All right. Let me show you how to do this in the Alex calculator. All right. The first calculation that you always have to do is the proportion itself. So good. Yeah. So come on by on Wednesdays. We'll be there. And if you're behind, well, you either can come on by or you can stop in on the Zoom, and we'll get you caught up to where you need to be. All right. So, but anyway, back to this one. Here we go. All right. So 288 of random sample, 375 letters. Based on this, compute a 95% confidence interval for the proportion of all letters mailed in the United States that were delivered the day after they were mailed. So 288 out of 375 were delivered the day after they mailed. Now, sometimes you have to watch these because it'll say like how many of them were not delivered today, and then we would have to do a little bit more math here. But this one's pretty easy. It's 288 out of 375. So we always start with that. 288 out of 375. Ta-da! There's our proportion, 0.768. All right, so we want to remember that. But the way that I do a confidence interval is we're going to take that plus minus, and then our confidence level, so 95%, so it's 1 minus 95.05, chop that in half, 0.025. So 0.025. So, and that'll give us our Z-score for this confidence level. Okay, and then we're going to take that, And then we multiply that by the square root of p hat, which is this guy right here, .768 times 1 minus .768 all over. And then this one's kind of tricky, so you got to do that piece. Then grab this like that, and hit your divide key, and now we're going to put our sample size underneath it, which is 375. The sample size is always the whole, so part whole, this is also your sample size, 375. Enter, and there we go. So, and you should always be decimalized, all right? So remember, they're proportions, and so if you get something that's like 1 dot something something something, you did it wrong, all right? So this needs to be lower than whatever your proportion was, all right? And this one here needs to be higher than whatever your proportion was, or p hat. If I hit undo, there's my p hat right there, .768, that first calculation I did. And so .768, and so this one, this is above, and this is below, okay? So 0.72, how many decimal places? 2. So 0.73, and this one is 0.81. 0.81, there we go, check. Ta-da! So let's do some more. Here we go. It's 275 individuals working in a large city indicated that 90 are dissatisfied with their working condition. Wow, that's lower than I thought. Based upon this, compute a 95% confidence interval for the proportion of all individuals in the city who are dissatisfied with their working conditions. So 275, 90 are dissatisfied. And so let's figure this out. So it's 90 who are dissatisfied out of 275 total. There's our proportion, our p hat. So now see how this one says carry your intermediate computations to at least 3 decimal places? That means this guy right here. So we can chop this all the way down to 3 decimal places. Okay, confidence interval. So that's my mean plus minus my z-score for 95%. So z 95, 1 minus .95 is .05. Chop that in half, .025. Here we go. So times the square root of my proportion, which is 0.327, times 1 minus 3.27. This piece here is also called Q. All right, so sometimes you'll hear it referred to as Q, but not in this case. Divided by our sample size, which was 275. 275. There. Oh, undo. See, okay, I got an undefined error here. That's because my cursor is right here. Okay, so if you actually hit your arrow key twice and get back out to the end here and hit enter. Oh, no. Wait a minute, what's jacked up here? Something's jacked up here. I think it's right here, actually. Hang on. Let's redo this piece. So 3.725 plus or minus z.025, arrow key over. That's the part that I didn't do right there. Times the square root. Yep, so that was a little bit jacked up right there. That's okay. .327 times 1 minus .327 and parentheses. Highlight this piece here under the square root. Hit divide by. And now my sample size, 275. Hit your arrow key twice. So you get the big cursor right there, enter. There we go. So sometimes it's a little picky. Sometimes it's a little picky. All right, here we go. .27 and .38. 0.27. Yep, and 0.38, 2 decimal places. Good. Check. Done. All right, one more. Here we go. And then we'll go do T-distribution. All right, 375 students, 315 said that they were non-smokers. So compute confidence interval proportion of all students in the university are non-smokers. Okay, so it gives us 315 non-smokers out of 375. So 315 divided by 375. There's our proportion, .84, really nice and easy. And our z-score for 99. So 1 minus 99, .01, chop in half, .005. .005, hit my arrow key over, get the big cursor back, hit my square root button, and my p hat, which is 0.84 times 1 minus .84. Grab this, hit my divide by key, and then my total sample size is 375. Arrow key over twice, 1, 2, hit enter, and there we go. So 0.79, 2 decimal places, so 0.79 and 0.89. And 0.89. Oh, didn't give me my 0 right there. There we go. Otherwise, Alex is going to yell at me. You don't get it wrong, but it does get mad at you. So, all right, here we go. Let's do another one. Let's go do T's now while we're at it. So this is use of the T distribution. This is exactly the one I want to do. All right, so this one's a little bit of a pain just because it throws in a stupid BS step in here. So with some of these, it gives you the data right here. The only thing that you need to pull from the data is the mean and the standard deviation. Okay, so you do need to have those two things. And so this is where scratch paper comes in handy. Let's see what kind of scratch paper I have here. Ah, this would be my utility bill that I just paid, so we will use that. So, all right, so for some of these, you have to calculate it. Some of them, it gives it to you. But other than that, you're going to do exactly the same thing, all right? There's only one extra step in these, and I'll show you that as soon as we get to it. All right, well, I mean, other than that, right there. So anyway, here we go. Start. The formula is exactly the same. Well, actually, let me show you the formula here real quick. Exactly the same right here. So it's going to be our mean plus our t-score right here times standard deviation over the square root of the sample size. Okay, and so our t-score right here, this is the piece that requires one extra step, and I'll show it to you as soon as we get there. All right, or t-stat. Sorry, it's not a t-score. All right, random sample 13 sold. Okay, so this one we don't have to do any of the extra calculations. They're going to be nice to us right off the bat and just give it to us. All right, so mean sale price of $280,000. So I take my mean, $280,000 plus minus standard deviation of 9,000 under the assumption that housing prices are normally distributed. Find a 90% confidence interval. So the next piece here is my t-stat, and so I'm going to use the 90% confidence interval, and so it's t. 1 minus 90, all right, which is .1. Chop that in half, .05 right there. So remember, I got to have it on both sides. Now, the thing that's new here is this, df, which is degrees of freedom. Whenever we use the t-stat, we have to calculate our degrees of freedom. Degrees of freedom is always your sample size minus 1. And so how many houses? 13 houses, and so 13 minus 1 gives us 12. That's your degree of freedom right there. And then arrow key over, and then I think we should do this in parentheses, but I don't think you have to. And so then it's my standard deviation, which is 9,000, divided by the square root of my sample size. My sample size, 13, right there. So degrees of freedom and sample size are two different things. You just use one to calculate the other. All right, so this one it is asking for sample size. All right, close parenthesis, done. All right, so nearest whole number, got it. So $275,551 and $284,449. There we go. Check. Ta-da! All right. So now when you do the quiz, and I think these are chapter 9, they might be chapter 10 quizzes, it doesn't tell you which one you're doing. Okay, so it'll say like in the other ones it's use of the standard normal, this one's use of the t distribution. The way that you tell whether or not it's a t distribution problem in there is that it'll have this piece right here where it says sample, okay, and then it'll give you the sample standard deviation. It will not give you the population standard deviation. So if it says sample like this and sample standard deviation like that, it's t distribution. So use this process on those. Okay, you'll get the hang of it. All right, here's one where it's going to give us the data. All right, so losers. All right, so fortunately this is really easy to do. So you take this data here, you send it to the calculator, and if you want the mean, you hit this button right here, X bar, okay, enter. There we go. And so on our first problem, X bar is 8. Okay. At least I think I do that. Maybe you do the X bar button first, then you send the data to the calculator. And oops, don't hit that and hit it. Okay, it doesn't matter which way you do it. All right, and so that gives you your mean, and then to get your standard deviation, you do the exact same thing, except for you hit this button here, SX. So S is sample standard deviation. All right, so S Send data to calculator, enter. There's our S, our standard deviation for this. 2.34, 3 decimal places, 345. There we go. Okay. All right, so now it wants to figure out for each HMO copayment is recorded results 90% kind of blah blah blah. All right, so nothing weird about this, and so we start with our sample mean, which was 8, and then plus minus on this one. T-score, T-distribution, or T-stat here with a 90% confidence interval. 1 minus 90 is 0.1. Chop in half is 0.05. Degrees of freedom. So how many of our sample? So we have 9 in our sample. So our degrees of freedom is 8 on this one. So it's always n minus 1. Okay, and then we take our sample standard deviation, which was 2.345, divided by the square root of whatever our sample size was, which is 9 or 3. You could just do 3 in there if you really want to, but that's okay. And there we go. So 1 decimal place. Why would we round a monetary figure to 1 decimal place? No one like spends $1.2 on something. It's $1.20, right? Okay, it is chapter 9. Got it. All right. So cool. So 6.5, and then this one here is 9.5. 9.5. There we go. Check. 2 in a row. Let's do one more, and then we'll go do that sample size one, and then we'll jump over to hypothesis testing, and then we'll do. Well, before we do that, we'll do a trivia here. All right, here we go. Toys, test 10 says the attention span 34 minutes. The test says 49 the temperature span with new toy. All right, whatever. So this one, they're going to give us the data. So attention span mean was 34 minutes right there. Plus minus T, and that's 99. So 1 minus 99 is 0.01. Chopped in half is 0.05. With degrees of freedom, how many kids? 10. So degrees of freedom, 10 minus 1 gives us 9. Okay. And then our standard deviation was 4 right there, divided by square root of our sample size, which is 10. Arrows twice, close parenthesis, ta-da. There we go. So 29 minutes. I think that's a little old. That's a little long. It depends on how old these kids are. So I think the rule out there is that like your attention span is basically roughly equal to the amount of years old you are. Well, 1 decimal place. So, you know, that makes sense. Yeah. So even in my case, I think about the longest lecture I can listen to is about 45 minutes, and so that's pretty close. Check. Done. All right, T distribution in the can. All right, let's do the easy one, and then we'll go do we'll do some trivia. So this is a choosing an appropriate sample size. So choosing an appropriate sample size, the formula is really easy to do because you're just going to reverse engineer this guy right here. Okay. So n is basically equal. Well, you're reverse engineering this, or where is it? This one right here. All right, but effectively it comes out to be this. Your sample size is going to be your z-score times your standard deviation divided by this e, which is going to stand for error, okay? And you square that whole thing. So it's really that easy to do. And you're going to ask me, well, what is error? Okay, error is the range, all right, of which you want your estimate. And so this one, 95% confidence in, that their estimate is within 1.5 minutes, okay? And so in order to calculate this one, it's really straightforward. Here's our Z value right there. All right, so, and that's going to be determined by our confidence level times our standard deviation divided by our error, okay, and then we square the whole thing, and boom, we get our answer. Now, there's one last trick to this, and I'll show that to you here in just a sec. So, but here we go. Those are all the only things that we actually have to pick out of here. So you start with your Z, so it's 95% confidence interval on this. And so our Z is going to be 1 minus 95.95.05 chopped in half, so 0.025. So Z 0.025, hit enter. Just start with that right there. And it says carry your intermediate confidence to at least 3 decimal places. You can do that in this case, but you don't have to. And so, because what I do with this one is just leave that number in there, and then I'll multiply it by your standard deviation, which is that guy right there, 2.15, and parentheses. grab the whole thing, divide by your error. So it wants it within, let's see. What? 95 is within 50 cents right there. So .5. Okay. Enter. And then just hit this square button right here. Bam. There's our answer right there. 71. Now here's the trick behind these. All right, when you're calculating a sample size, it needs to be in an integer, okay? And so it needs to be the next whole number, and it needs to be the next highest whole number. So you don't round this down. Even though this is 71.02, you always round this up, okay? So because we can't have a .02 person, but if we round it down to 71, we don't have enough in the sample size to actually do this one properly, okay? And so you have to round this up, and then so it's going to be 72 in the sample, okay? Ta-da! All right, that's not intuitive, but this is like one of the 2 problems in Alex that works like this. I think we already had the other one way back in the day. All right, so but that's how you do that. All right, let's run through it again here real quick. All right, so we start with our confidence level, so which is this guy right here. So 90. So 1 minus .9 is .1, chopped in half is .05. Bam, right like that. Okay. And then multiply that by your standard deviation. So, which is right here, standard deviation, 24. Okay. Enter. Divide that by your error. So it wants it within 4. That's that right there. Take that, square it, bam, and round this up. So it's 98. 98. Check. Dunzo, dunzo. Don't even have to read the problem. Just have to pick out the information. So next one, confidence level 95, Z.025. Okay. So enter. And then take that, multiply it by my standard deviation. Where's my standard deviation? That's the 3. Use the value of 20 for population standard deviation. 20. Divide that by my error, which is within 3. There's my answer. Well, no, we got to square that now. There's my answer, 170, but I always got to round it up, so it's going to be 171. There we go. Oh my God, I just totally fat fingered that, didn't I? You guys probably watched me do that too. Like, Pat, you moron. All right, fine. I guess I'll do one more. All right, so here we go. 95%. So Z is going to be 1 minus 90 is .025, right like that. Okay. Multiply that by my standard deviation, which is right there, 29 minutes. Okay. Divide that by my error. I want it within 5. Okay. Square that. Bam. 129. Round it up. It's 130. Don't fat finger it this time, dude. Dunzo, dunzo. So that one, honestly, I think that one's the easiest out of all the like confidence intervals ones. If you get that one, there is a tab on my spreadsheet that you can totally use for that if you're a little confused on things. But honestly, I think you can do it fast enough with the Alex calculator. But that will do it for confidence intervals. That's the last we'll see of that for quite some time, even though we don't have that much time left in the class. All right, so food trivia. Let's see what we got. So there was one that I did a couple years ago that was all about, what was it? Like, it was all breakfast cereal trivia. But that website is not, I can't find it anymore. No, I want the answers. Stop that. Let's see. What do we got? Let's try this one. That's dumb. Let's see. Oh, here's a good one. Food trivia. Coca-Cola's headquarters is in what American state? So, where is Coca-Cola's headquarters in the United States? So, I had forgotten about this. That's true. This is actually where it came from, too. What U.S. state did Coca-Cola come from? Their headquarters is still there. Which one is it? This isn't really a food. Well, it kind of is a food question. So, but it's also maybe a little bit of a pop culture question as well. So, where does Coke come from? What U.S. state? You got it, Squidson, Georgia. Yes, absolutely. So, yeah, not just the headquarters there, but I think up until not too long ago, it may be still in the case, it's like the largest bottling facility in the entire world, if I'm not mistaken. I don't know. I know you could go and take tours of it um, at one point in time. So if you're going to do that, though, I would recommend. No, I'm not going to make recommendations about travel on this one. So that's okay. All right, we'll do some more food trivia here in just a sec. All right, but let's dive into hypothesis testing. All right. And so if you knock out all the confidence intervals ones, you're going to be looking at your pie. You're going to be like, what the hell? All right, because I got a lot more blue stuff to do here, but where is it? It's locked behind this question here. No, not this one. No, not any of those. This one. Determining the null and alternative hypothesis. All right. And so when we get into hypothesis testing, we're actually going to use some of the stuff that we just talked about in terms of confidence intervals, calculating either a z-score or a t-value, or in some cases chi-square down the road. I don't think those are in this chapter though. Those are later. To make a statistical determination about whether or not something is true. All right. And so in a hypothesis testing, what we almost always do is we ask basically a very theoretical question, and then we use statistics to prove it. And the theoretical question that we almost always ask in hypothesis testing is this one different than that one? Okay, and we use statistics to prove that. All right, and so that's what we're going to do. And so when you actually set that up, you will set up what's known as a null and an alternative or an alternate hypothesis. You'll hear it a lot of different ways. Okay. And so, like, for example, the breaking strengths of cables produced by a certain company are approximately normally distributed. So that's very important. We can only do this with normal distributions. So the company announced that the mean breaking strength is 2,200 pounds with a standard deviation of 186. A CPA complains, or Consumer Protection Agency claims that the actual standard deviation is much higher. Suppose that the consumer agency wants to carry out a hypothesis test to see if its claim can be supported. So state your null and your alternative hypothesis. Here's how I want you to think about it. Null hypothesis is no, we cannot prove this. Okay, so there's not enough evidence to actually prove this. And so whenever you build a null hypothesis, it's like, no, there is no difference. Okay, it is not what we are trying to claim is not true. Okay, or we can't support it. The alternate hypothesis is always what you're trying to prove. It's your claim. Okay, so when you do these, always start with your alternate hypothesis. Pick out that, all right, and then your null hypothesis has to cover all your other bases. Okay, here, I'll show you what I mean with this one. Really, really easy breezy. All right, so last year's mean hourly wage in dollars for all hospital clerical workers in the state was $7.75. That sucks. That's terrible. So an administrator for the state believes that this year's mean hourly wage for hospital clerical workers is greater than last year's mean. She hires statisticians to sample a number of hospital clerical workers and carry out a hypothesis test. Okay? And so here's your claim. An administrator for the state believes that this year's mean hourly wage is greater than last year's. Okay, and so that's our claim. That's our alternate hypothesis. And so she says that mean, this is mean right here, mu is mean, is now greater than $7.75 an hour. And so your null hypothesis, H0 or H naught, all right, or H null, that's all the same thing right here. This one's usually called H1 or HA, okay, for alternate. So it has to be everything except for this, okay? So this is where that mutually exclusive thing is going to come back to haunt you a little bit. So what would be mutually exclusive? It would be, well, if this one's greater than, then this one has to be less than or equal to $7.75 an hour, okay? That's how you do these. All right. So very, very important. You'll be doing a lot of these over the next week. All right. So let's pick out the claim. We have reason to believe otherwise. Okay. And so that's our claim right there. And so they said that the portion of the high school students in the United States who use computer is at most 71%. We believe that is false. Okay. And so be careful with this one, because since we believe that this is false, this is actually our null, and our claim is that this is not right. Okay, and so this is proportion. All right, so always pick out your statistic right here. It says proportion. Proportion is P. Okay? And so we believe that the proportion is not this. And so they say it is at most 71%. And so we would say that it is greater than 71%, right? 71%, dot 71. And then, of course, we got to use everything else to cover our bases. They say that it is at most. So that would be less than or equal to dot 71. There we go. Check. Ta-da! 2 in a row. So you do have to, like, you might jack a few of these up. It's okay. Just understand that usually if you're putting a greater than, less than, or equal to in this one, that's probably not right. Yours is going to be greater than or less than, usually in the alternate hypothesis. Okay? Unless it says different. We haven't gotten one of those yet. So an independent consumer group published its group findings in lifetime, blah, 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 blah. Big corporation claims that the variance of light bulbs is less than blah, blah, blah. So we want to see if they're correct. Okay, and so that's our claim right there. So they say that the variance, and this one's tricky because you have to know what the symbol for variance is. If you get the variance one, so remember that standard deviation is just the square root of variance. And so usually we use this as standard deviation, but since we're talking about variance, it's actually the square of this, okay? And so variance is always sigma, and then hit this button here, squared, like that. So they think their variance is less than that, so they think variance is less than 14520.25, and so this one really easy, same thing, variance, okay? Of course, we got to cover all our bases, so that'd be the opposite sign here. Greater than or equal to 14520.25. There we go. Check. Ta-da! Dunzo, dunzo. All right, so that's null and alternate hypothesis right there. All right. Oh my gosh, it keeps trying to throw me into stuff that's way down the road. But look at that. That unlocked 4 new problems right here. And so these are the 3 that you'll be doing hypothesis testing in. Okay, these should be chapter 10 problems, and they'll unlock the chapter 11 problems if I'm not mistaken. Okay, so which are exactly the same. They just involve an additional step. All right, we're not going to be able to cover those today. We will do so after you get back from break. Because if you get these crushed out, then they're pretty easy. Okay, so but we will go through all of these here today. All right. Well, we'll go through this one here today and this one. So if you do these 2, then these aren't that hard. And I already have videos up on these that'll show you how to do them. This one here and this one here, they're not too bad. They do involve a little bit of math, but I'm going to show you the easy way to do these and the Alex way and the easy way. All right, for both of these. But before we do that, let's do another food trivia question here before we run out of time. So let me see. I am not a real fan of this site, so let's go find a different one. Let's try this one. Nope. Nope, you pissed me off with pop-ups. Let's try this one. Here we go. Let's see. No. Oh my gosh, I don't know if this is right. Canola is an abbreviation for what? I did not know canola was an abbreviation. Canola is an abbreviation for what? Oh man, I don't know if that's true or not, but we're going to throw it out there. I did not know that. So canola is an abbreviation for what? Huh. I thought it was just called canola. Huh. Yeah, I mean, all right, so yeah, all right. I don't know who to give it to here because yeah, apparently it is Canadian oil or Canada oil. Um, Canada oil low acid. Yeah, I think we're gonna go with that, Guts. Squid said I'd give it to you, but you already got Georgia, and so you're good for the day. I can't give you more than one in a day. And so um, yeah, Canada and Ola. That is what it's made of. Oh, okay, got it. Rapeseed. I don't know. Yeah, I did not know that. That is, I thought it was completely like its own product. I didn't realize it was Canada oil. All right, so fine, Guts. We'll give that one to you, and then Matt, you said Canada and Ola, which is which I also think oil low acid. All right, as well. So I'll give it to both of you guys right there. We're gonna dish out points to everybody today. So, but I totally did not know that. So I thought it was just like, I didn't realize it was a Canadian product. So, and I mean that's true. I mean I know ketchup chips come from Canada, and maple syrup comes from Canada, but and hockey kind of comes from Canada. I don't know, but I did not know canola was a Canadian thing. So yeah, no, I don't know, man. It's totally cool. All right, so here we go. Let's do some of these. The next one that you want to do after you do that, building the type one, I mean the null and alternate hypothesis is this one, type one and type two errors. This is a very complicated problem that a lot of people get wrong. All right, I know I already have a video up on this one, so if you're jammed up on it, I probably did a better job of explaining that on that video than I have anywhere else. But we'll try it again. All right. So you have to understand that when we're doing hypothesis testing, there are two possible errors that you can commit. They're called type 1 and type 2. All right. So a type 1 error, also known as a false positive, is when I make a conclusion that the data actually cannot support. Okay. So I make a claim and I say, okay, this claim, according to the claim that I made and the data that I have, this is actually true. But then we would turn around and pull another sample and that one would be false. And so obviously your initial assessment was not correct. Okay. And so that's a type 1 error. Type 2 error is the opposite. It's called what we call a false negative. Okay. It's when I can't make a claim, but I actually do have the information to be able to make that claim and substantiate it. Okay, so like this is the way that I want you to think about it. And this is a little bit morbid, but I have a little bit of authority to speak on this one. All right, so, but a type 1 error is when I tell you you have cancer, but you don't, okay? And so you're going to go through the whole rigmarole and stuff like that, but ultimately, and down the road, it turns out you don't have cancer, and so you didn't have to go through all that, all right? A type 2 answer is when I tell you you don't have cancer, but actually you do. And so a type 2 error is much, much worse than a type 1 error. Okay, because it has very negative consequences out there in the real world, and it is something that happens with enough frequency that it's something that in more advanced statistical analyses, we would try and avoid that one before we avoided the first one. Okay. And so in this problem, it's going to ask you a series of questions here, and this one does get confusing because it does become fill in the blank. Let's just dive in and do one here. And so just remember, type 1, I tell you you have cancer, but you don't. Okay, which means that I reject the null hypothesis and confirm the alternate when actually the null hypothesis was correct. And type 2 errors, I tell you don't have cancer, but you do. That's when I fail to reject the null hypothesis, but actually I should have. Okay? And so that's how these goes. All right, what are the null and alternative hypothesis? And so this is why you do this one right after you did the last problem that we just did, because this is exactly the same. All right, coin operate, blah, blah, blah. This is 7.18 ounces of cup per coffee. If its defense is more than that on average, corporation may lose money. And if it's less, then the customer may complain. Believing that the minimum amount of coffee dispensed with the machine is greater than $7, so Big Corp plans to do a statistical test that claim that the machine is working as designed. So they think that it's actually more than that. All right, and so they think that it is greater than 7.1 ounces, which means this one is going to be less than or equal to 7.1 ounces. Okay, and so that's our claim, and so our null has to cover all our base. In the context of this test, type 1 error, remember, type 1 error, I tell you have cancer, but you don't. So type 1 error is rejecting the hypothesis, rejecting the null hypothesis. Here's your null hypothesis. So just take a look at this, punch that in there, 7.1, when in fact it is less than or equal to 7.1. Now you're going to look at this and be really confused. Be like, well, this is the same thing. Okay, but think about this. Type 1 error is rejecting the null when the null is true. Okay, so it's just repeating itself here. Just be careful. Whenever you get this one that says type 1 error, this and this is almost always going to be the same. All right, suppose that big decides to reject the null hypothesis. Whenever you reject the null hypothesis, you do have the possibility of committing a type 1 error. So null hypothesis, you don't have cancer, but I told you you did. Okay, and so that's the kind of error that I could be making. Check. Ta-da. Okay, let's do more. All right, this problem is really, really hard. Yes, if it differs, then you use equal to, okay, or not equal to. Okay, we haven't run into one of those yet, but yes, when it says differs, we might get one of those. All right, so let's see. Some college graduates important the full-time work 40 before we expect the mean number of hours per is less than 40. And so we think it's less than 40. We want to do a test. And so is less than 40. This one would be greater than or equal to 40. Got to cover all your bases. Type 1 error is rejecting the null hypothesis, which is this one right here, greater than or equal to 40, when in fact it is greater than or equal to 40. Suppose that we decide to reject the null hypothesis, we might be making a type 1 error. Whenever you reject the null, you might be making a type 1. There we go. All right, 2 in a row. I know I might be making this one look easy and you might be like really frustrated with it. That's just because I've gotten this problem wrong many times. All right, here we go. Managers in an automobile manufacturing plant would like to examine the mean completion time of assembly line operation. Past data indicate mean completion time is 41, but they think it's decreased. All right, and so they think it's decreased, and so they now think that mean is less than 41. When in before it, our null would be everything else too is actually greater than or equal to 41. Okay, type 1 error. So I didn't get a single one that's type 2 here. We might just do another one. Rejecting the null, so which is greater than or equal to 41, when in fact the null, which is greater than or equal to 41, is true. Okay, and so that's why you always do this part first, because type 1, rejecting the null when the null is true. Type 2, failing to reject the null when, in fact, the alternate is true. Okay? Suppose managers decide to reject the null hypothesis. Whenever you reject the null, you have the possibility of committing a type 1 error. There we go. Check. Oh, what did I get wrong? Type 2. Type 1, greater than or equal to 41, when, in fact, mu is greater than or equal to 41. Response to number 2 is correct. Rejecting the null hypothesis when in fact the null is true. Wait a minute, I'm not sure what's wrong here. Type 1 error. Tell you have cancer, but you don't. So rejecting the null. Managers plan to perform a statistical test. So they think that one's true. 38 means standard deviation. We don't need any of that information. Past data indicate that the mean completion time is 41 minutes. Greater than or equal to 41. Oh, see, look at that. Look at that. Greater than or equal to, and this one just says greater than. So just a little change right there. They got that one wrong. All right, I guess I gotta show you another one. Just be careful with these, all right? So here we go. Union of restaurant and food service workers would like to estimate this year's mean hourly wage of the food service workers in the U.S. Last mean's wage was $8.16. That's terrible, man. There's a reason to believe that this year's value is different from last year's. All right, so reason to believe this year's value is different than last year's. All right, so when it doesn't say greater than or less than or more than or fewer than or something like that, All it says is different. This is technically a two-tailed test, all right? Meaning that we're not making a claim that it's, well, it's greater than, so it's on this side of the distribution, or it's less than, so it's on that side of the distribution. We're saying it's different, all right? And so that would be a two-tailed test. It could be on this side or that side. Either one of them would satisfy a requirement of being different, okay? When you do these, they're much easier, okay? So because whenever it says differs like this, and so we want to see if things have changed. So when they say different, we say it's not equal to whatever it was last time, $7.86 right there. And so this one, our null hypothesis would be like, nope, it's exactly the same, which would be equal to, right, like that, 786. Make sense? Okay. Or no, 816. So last year's 816. See, I almost got jacked up. I was using this year's right there. And so this is just the sample. We go off population. So 816 right there, 816. There we go. In the context of this test, a type 2 error. Okay, so a type 2 error, I tell you, you don't have cancer, but you do. And so I fail to reject the null hypothesis, which is this guy right here, equal to 816, when in fact it is not equal to 816. So failing to reject the null hypothesis when the alternate is true. Here's my alternate. And so see how those match like that? There we go. Supposing the union decides not to reject the null hypothesis, whenever you fail to reject the null hypothesis or decide not to, you have the possibility of committing a type 2 error. And so remember that. If you reject the null, you say, nope, it's different. Okay, that's always, you have the possibility of committing type 1 error. If you fail to reject it or you decide to retain it, that's always could be associated with the type 2 error. Okay, there we go. They are mutually exclusive. Okay, all right. Dunzo. Hope that helps. Yeah. So, and hey, look at that. You know, so we got one in there that kind of showed you something that was a little bit different. All right. So, let's see how many questions we've done. 2 food questions. So let's do one more Alex problem, and then we'll do one last food question here. Okay, and so let's do this one. Hypothesis test for the population mean. All your hypothesis test problems from this point on time on are going to look like this. Okay, so now in order to conduct a hypothesis test, we have to do all the things that we just talked about. So first thing is we're going to state our null and alternate hypothesis. Then we're going to determine the type of test statistic. Now it's easy in this one because it's going to say right up here, this is z-test. So we're going to use the z-stat. All right. If it's this type of problem, so where you know the population standard deviation, you're always going to use z. Z is the best test to use. Okay. If you don't know the population standard deviation, but you do have your sample standard deviation, you're going to use t, which is hands down the most common one that we use. If it's a proportion, you get to go back to the z-test. The reason why you get to do the z-test with proportion is because it's part of a whole, and so it's always normally distributed. Okay, so everything fits under one. All right, so those are the 3 types of problems that you're going to see here in this chapter. All right, so but when you're just in Alex, it tells you right here, so you just put that right there. Okay, and then you find the value of the test statistic. In order to do that, you just use the z formula. Right, like this. All right, so this is x bar minus mu all over standard deviation divided by the square root of n. Okay, x bar is your sample mean divided by your population mean all over population standard deviation divided by the square root of your sample size. Boom, there's your test statistic right there. Okay, all right. And then there's 3 different ways to make conclusions. Well, there's 2. So you either use what's known as the critical value or the crit value method, all right, which is where you use a cutoff value like this. And so say our cutoff value is 1.96. We do that in the Z calculator using this guy right here, the Z box, okay? And if our value was lower than that or fit in between here, then we could not reject the null. If it's outside of here, then we would have to reject the null. The other way you do it is by using the p-value method, okay, which is the way that we do it in the wild. So that's this button right here. We use probability. What's the probability? And as long as the probability of getting that would be less than whatever our level of significance was, then we would reject the null. I know that's a little complicated, but let me just show you how to do these, okay? So and this is the one, if you get this one down, all right, so a lot of the others will start making sense. Okay, so here we go. A furniture store claims that its specifically ordered product will take on average mean 42 days to arrive. This is obviously not Amazon. Standard deviation of these waiting times is 5 days. Okay, so we have population standard deviation. We suspect that the special orders are taking longer than this. To test this suspicion, we track a random sample of 18 special orders and find that the order took a mean of 45 days to arrive. Assume that the population is normally distributed. Can we conclude at the .01 level of significance that the mean waiting time on special orders for this furniture exceeds 42 days? Okay, and so we think that mean is greater than 42 days. All right, which means that we're going to reject if it's less than or equal to 42 days. Okay, makes sense? All right, so type of statistic, Z. Find the value of the test statistic. Really easy to do here. So we take our sample, which was 45, subtracted from our population mean, which was 42, or subtract our population mean from that. So this is X bar minus mu right there, divided by our standard deviation, which is 5 days, enter, divided by the square root of our sample size, which was 18 right there. Bam. There's our test statistic right there. That doesn't look right, but it might be. 0.14. Let's just punch that one in there again. So real quick. So it's 45 minus 42. Okay. Gives us 3 divided by our standard deviation, which was, where is it? 5 days. Okay. Divided by the square root of our sample size, which was 18. Bam. Yeah, okay. So find the p-value of this. All right. So when we get a p-value problem like this, all you have to do is take this and then just punch it in right like that. Okay. Bam. There's our p-value. 0.55. Okay. So, and then 3 or more decimal. 556. There we go. This might not be right. I might be jacking something up here. I don't think so. And so when you do the p-value method like this, and so p less than or equal to, or greater than, probably find a z that's greater than or equal to that, that's your p-value right there. All right, so the way that this works is that when you're using the p-value method, this has to be less than whatever this is in order for you to reject the null hypothesis, okay? Meaning that oh no, so this one's 42 and we found one that's 45 days. That's extremely rare, you know, but honestly, this kind of makes sense. 42 days with the standard deviation of 5 days. And so standard deviation, you know, would cover 5 more or 5 less than that. And so, you know, really when it comes down to it, the probability of having one taking 5 days is, probably about half, you know. And so in this case, no, we cannot conclude that it exceeds 42 days. So 45 is just not enough, all right, in order for this one to be extremely rare. My whole answer is incorrect. What did I tag up here? So mean equals 42. Taking longer, greater than 42, less than 42. Can we conclude the mean waiting time? All right, so I jacked something up here. Let's see. So 42, less than 42, 2.546. All right, so this is the piece that I screwed up. What did I do wrong here? So maybe you have to do the whole thing. So 45 minus 42 gives me 3, divided by 5, divided by the square root of 18. Yeah, there we go. Yeah, all right, so you can't enter these one at a time. You got to do the whole thing. All right, so I thought I was doing that right, but that p-value just seemed kind of weird. So, and see, notice that jacked up my entire answer because that would change this, which would change this, which would change these. Okay, so let's do another one here real quick. All right, we'll be a little bit more judicious. We had it right up until that point in time. So here we go. The number of miles driven annually mean on cars is less than. Random sample had a mean is known population standard deviation. Number of miles is 1,100. Is there support to is there support for the firm's claim at the .1 level of significance? So so they think it's less than this, and so they think mean is now less than 12,780. And of course, the null hypothesis would be mean is greater than or equal to 12,780. So this is a z-test. Find the test statistic. And so we take our sample, 12,499, subtract our population, 12,780. Okay, and then divide that by the square root. Or divide that by the standard deviation, 1,100. And then divide that by the square root of our sample size, 50 cars. Bam, there we go. Test stick negative .1086. Okay. Find the crit value on this one. All right, so this is a less than test. And so on this one, in order to find the crit value, all we're going to do is Z and then our level of significance .1. So we're looking for anything that's less than .1. If we punch that one in, sorry, my bad. So Z box here is a right-hand lookup. So if we're looking at the left-hand side, we would take this .1. And so we're looking for anything less than .9. So there we go, right there. That's going to be our value. If these two don't match, so if this one's negative and this one's positive, or this one's positive and this one's negative, you probably did that backwards. Okay, and so focus on this one, then make sure you get that one right. Just remember, this is always a right-hand lookup, okay? And so if you're looking for something greater than, then you can punch it in directly. If it's less than, then it's going to be whatever, like, the complement of this is. So .1 would be .9, okay? And so here we go, negative 1.28, 3 decimal places, 282, okay? So now, rejection region, when you do one like this, and this is the old school way to do it, nobody does this out there in the wild anymore. We always use p-value just because it's easier. But with this one, think about your distribution. It's like this. These are z-scores right here. And so our cutoff value is negative 1.28. Here's our mean. Our cutoff value is negative 1.28. The z-value, z-score for our sample is negative 1.80, which is further less than this, further to the left than this. And so this is really rare. Okay, so this is definitely rare, and it's definitely, you know, we would have a probability of less than 0.1% of finding one that fit this way. And so in that case, the answer is yes on this one. This one's funky because it's outside of this. There we go. All right, cool. Next, let's do another one. Okay. Manufacturer claims mean lifetime mu of the light bulbs 42 months. Value of the test statistic. Yes, we'll do it here right now. So with this problem. 42 months. Standard deviation of those lifetimes is 6 months. 25 bulbs are selected random. Mean lifetime found to be 43. And so, assume the population order. Can we conclude at the 05 level, say the mean lifetime span differs from 42 months? So whenever we get differs in here, that is going to be a two-tailed test, all right? And so whenever you see this keyword differs, this part gets really easy. And so they think that mean is not equal to, it differs from 42 months. And then, of course, this one is like, nope. Yep, it still is 42 months. Determine the type of statistic, Z. All right, here, value of the test statistic. Real simple, straightforward. Take your sample, which is 43 right here. 25 bulbs are selected at random, so that's the sample. Mean lifetime is 43. Subtracted from your population, which is 42. Okay, so it's X bar minus mu, so sample mean minus population mean. Hit enter. Divided by your standard deviation, which is 6 months. All right, so 6 months. Oops. 6 months divided by your sample, square root of your sample size. Square root of sample size. 25 bulbs. Right there. That's my test statistic right there. Okay. 0.8333. 3. Whatever. Let's see if Alex takes it. All right, so that's your test statistic right there. Okay. When you actually go through this entire process and do it that way, then you'll come up with the test statistic. And look at this. 43 isn't that far off of 42. And so remember this test statistic here, this is a z-score. All right. And since they're not that far apart, this one's actually pretty accurate. The further apart that your sample is from your population mean, the higher or lower this number will go. Okay, so it'll get up to like -1, -2, -3, and remember, -3 would be 3 standard deviations away from the mean because again, this is a z-score. Okay, find the p-value for this. Just punch it in like that. Bam. There we go. Oh, actually, that's not right. We actually have to take that. Oh, this is the hard one. I forget how to do this one. Okay. So we have to take that because that's our p-value right there. And I think we have to chop it in half. right? Divided by 2. I think so. Yeah. I think so. Oh no, there's another trick to this one that I'm forgetting. Arg, I'm gonna get this one wrong. Dot 3988. There's something about this that I'm forgetting. When you get a p-value on this one where it's a two-tailed test, yeah, you have to take the value. I think it's 1 minus the value. No, it's yeah. Arg. Oh, I can't remember. So we're going to get that one wrong. So that's okay. We'll just go ahead and punch these in here. Let's see what your answer is incorrect. Yeah, I know. Proceed. All right. So what parts do we got? We got that right. So p-value we got wrong. And that's because, okay, yeah, that's the trick on this one. When you get a two-tailed test on this one where the p-value is, we're asking for the p-value on a two-tailed test, you got to remember that this z-stat, the z-score that you figure out is on both sides. It's positive and negative because it's on either side. Okay, because that's how a two-tailed test works. Whenever it's different, then it can be up here, it can be down here. Both of those would be acceptable. Okay, and so you have to take these two and add them together. All right, and so it's the probability of the negative value and then probability of the positive value added together, and that's how you get that. Okay, that is a little frustrating. Okay, so if you get this problem, this is going to give me an opportunity to show you one of the tools that you can use. If you're not getting these, okay, and if you're really having some difficulties, getting through the entire thing, head on over here. All right, course modules. This is the last thing I'm going to show you today. And if you stuck around this long, this is going to be worth your time. All right, go down here, hypothesis testing. And here's a hypothesis testing website. You can use this one or this one. This one goes down a lot, so use this one. And here's your site. It's Inferential, okay, which you can use to do hypothesis testing and some of the other stuff that we'll see in the future. Okay, and so they have 1 sample test and 2 sample tests. Okay, for both of these. All right, we're not doing 2 sample tests just quite yet. Those will come up in a week or two. All right, and so you can use this site for those as well. All right, but in most cases, you're going to be either doing a 1 sample Z test or a 1 sample T test. And so these ones are Z tests. Okay, and so you have to go through here and actually figure this stuff out. It's really not that hard, but it's asking you to do the exact same thing, all right? So it's giving you what's your significance level, what's your hypothesis, what's your sample size, and then it's going to ask you your proportions on this one. You don't really need to do this as a proportion, but if you are doing it as a proportion, you can do that as well, okay? You can punch in straight up values in here as well, okay? So here we go. Let's try one. Furniture store claims that specifically ordered product will take on average 35 days. Standard deviation of these waiting times is 8 days. We suspect that the special orders are taking longer than this. Test the suspicion. Random sample is 17 orders and find that the orders took a mean of 36 days to arrive. If it's more than 35 days, so that's our claim right there. So we're thinking mean is greater than 35, and so of course our null is mean is less than or equal to 35. Z-test. So let's go in here and find the value of this test statistic. We got to pull this information out of here. And so let's see. There is a way to do this on here. This is Z-test for proportion. I don't think you have to do this as a proportion. Hang on just a sec. Means. Single mean. This one. You can do this one right here. No, that's a T-test. Normal distribution. Gosh dang it, they changed the site since I've been on here long. I think you can use this one, but you just don't have to do it as a proportion, if I'm not mistaken. Let's find out. Okay. Oh. So my null, which is my population, which would be 35. I'm not sure if this is going to work on this one. 35 days. Yeah, okay, shoot. So you used to be able to do this one, so it wasn't a proportion. They keep changing some of the stuff up here. So this one will help you with some of the other stuff down the road, but it's not really going to help you much on this one because you got to use Z on this one. Hang on. Let's try this one. So now the cool thing about this site here, MathCracker, is that there is a test for literally there is a calculator for literally every problem that you'll see in hypothesis testing. It's just like this site is freaking slow sometimes. And so Here we go. Let's go to, you want to do online calculators on this one. Hang on. And we want to do, because that one took you to the t-test. Hang on just a second. I got to reorganize myself and think about where I'm here. T-test, no. Maybe it's hypothesis test. Yep, here we go. No. All right, let's start over. Online calculators. Is there a search bar? There is. Z-test. Let's try this. And of course, slow. Here we go. Oh my God, look at all the stuff that's on here. All right, so they've reorganized this site since I've used it the last two. So I don't want to sit here and burn up all your time trying to figure out. Oh, let's try this. No. No. Ah, shoot. Well, the calculator's in here somewhere. I just don't know where it is. Here we go, statistics calculators. So click on this little button right here. Go over here to Z-test calculators. There we go. All right. So, and it's going to have the 4 different types of calculators on here. You will use all 4 of these, all right, if you decide to use this site. So the one that you're going to want for today is the Z-test for one population means. Click on that, and then you have to set up your hypothesis. And back over here, our problem. Our hypothesis is mu is greater than 35. And so go back over here. We're going to say mu greater than. This one has to be less than or equal to. And then the hypothesis mean right here is 35. All right, so 35 days to arrive. Our sample is 36. So go back over here. Sample mean is 36. You got to put in your population standard deviation. Our standard deviation on this was 8 days right there. Go in here, 8 days. Sample size, got to pull that information out of here too. Let's see. 17 right there, so 17, and then your significance level or your alpha is given right there, so 0.05. And so we want to do this 0.05. Go down here, click solve, and we wait. And that's the problem with this site, is sometimes it times out on you. Sometimes you get lucky. If you're doing this in the afternoon, especially on a school day, it can take a long time. But look at that. It didn't take much more than about 30 seconds there, and it gave us all our answers. Now, the cool thing about this site, unlike this other one, all right, when this one's actually working, all right, it gives you every piece of information that you need. Here's your null and alternate hypothesis. Make sure it matches. Okay, what you got here? Here's your rejection region. So if it asks you for the crit value, there's your crit value right there. All right, test statistic. Here's our actual test statistics, so 0.515. Let's go back over here to Alex and punch that in, 0.515. Our critical value is this guy right here, 1.64. So 1.64. Can we conclude that the mean waiting time on special orders at this furniture store exceeds 35 days? Well, no, because this is way less than that, and we're doing a greater than test. All right, but if that confuses you, and the reason why I like this site is you go down here and it says, oh, no, H naught is not rejected. So, and it tells you exactly why. Now, this is a little bit of a lengthier way to do these problems, but at the same point in time, it's kind of foolproof. See? There you go. All right. Again, it just takes a little bit of time. You do have to make sure you set up the information correctly in the site up here, all right, in terms of setting up your hypothesis. You got to have the null and the alternate hypothesis, and all these figures have to be exactly correct in here. But this site will give you the right answer every single time as long as you do all those things. Again, it's just a little frustrating because sometimes this one goes down. And so if you're a night owl like me and you're up at 3 a.m., you won't have a problem. If you're more of, you know, like, oh, I want to work on it on Friday afternoon, you might have some problems with this website, okay? In which case, you can always use the method by hand as well. And even though I jacked it up a little bit today, I do have videos up on each and every last one of these different types of problems. And so please jump in there, dive in, get to it, and knock out some hypothesis testing. With that being said, I have soaked up all your time today, and so I owe you one last trivia question here. And so let's do this one. Let's see. Let's see. Is that true? Oh, no, I don't know. Uh, I have no idea. If you guys don't even know any of this, let's see. These are all like state-based questions. Like, okay, I don't know if this is right. What is the state dish of Texas? I didn't know Texas had a state dish. Oh, it makes me wonder. What's the state dish of Colorado? Please tell me it's not Rocky Mountain oysters. So, but okay, we'll see if this one's correct. What is the official state dish of Texas? Go for it. Mm. For anybody who's still with me there today, and we'll see for a free quiz, official state dish of Texas. So we'll see if that's correct. Yes, Eric, you got it. So, yep, chili con carne. So we'll take your answers since you're still here with me today, and so that makes it, I think, officially all four of you who are here on the stream with me today. I think you all got one. Well, maybe Morgan didn't get one. That's okay, Morgan. If you're still with me here, yeah, okay, I'll give it to you too, buddy. So thanks for being here with me today. Yeah, I got another live stream coming up in just a couple minutes, so. I got to log off here, but at the same point in time, use these websites in order to get through the hypothesis testing, or just walk through the process on your own. I think it's actually faster once you get kind of the formulas down, stuff like that. No, you're fine, man. So take it. If you get a little bit jammed up on some of these, though, ping me. All right. So there are YouTube videos up on each and every last one of these. They will help you. But if you do get a little bit jammed up on the rejection region and stuff like that, just email me. I'm here to help you. Okay. Other than that, we'll see you guys on Wednesday. So I'll be back for a lab, and we can do some hypothesis testing there if you're jammed up on some of these as well. And so we'll see you then. Watch for the link. A couple minutes before we get started on Wednesday, and we'll help you chew through it. All right. See you then. Take care now. Bye. You bet. See ya.